So hi everyone. So I'm already like very tired. So like if I'm a little bit low energy, that's because of that.
Have some chocolate.
So yeah, my name is Guilherme, if you can pronounce it. I am a KICP postdoc fellow at U Chicago. I work with both Alexes. It's Alex G and Alex Wagner that. But the work that I'm going to present here is mostly in collaboration with like other postdocs and also surveys that are being conducted outside of U Chicago actually. And so yeah, the topic is like dwarf galaxy archaeology, from faint Milky Way satellites to the Magellanic clouds. So I really wanted to go into like this topic of dwarf galaxy archaeology and what it means and what we can learn out of it. But also like probing like different environments in terms of like the Milky Way satellites, like from the low mass dwarf galaxies to like the monstrosities like the LMC. So yeah, just gonna start with like this pretty picture right here. So yeah, so this is the Milky Way. So this is an image reconstructed out of Gaia data. So essentially, this is a weighted histogram of like sources from the Gaia data. So what this is showing here is the Milky Way in the middle, but also, so yeah, Gaia is this this spacecraft right here. Some people say that it looks like a trash can. And after you see it, you can unsee it. So this is the Milky Way. So, but around the Milky Way, and like Gaia was like really designed is this astrometric mission that is like put in space, and it was really designed to study this thing right here in the middle, which is the Milky Way. And especially to what Gaia does for us is like really to obtain astrometry for like many sources on the sky. So by astronomy, I mean parallaxes and proper motions and also positions on the sky, like very precisely, and in a scale that was like never achieved before. So you can really use like this Gaia mission to probe like a meaningful amount of stars in the Milky Way. So this figure right here has about 2 billion sources. And out of the data in Gaia, there's like about 1 billion stars.
Sorry to interrupt, but we're not seeing your screen on Zoom. We're only seeing a title slide. So I'm not sure. Yeah.
That is true. So what I can do is like to stop sharing and sharing it again. Let me share again. Oh, I did this. What about now?
All right. Yeah, that's perfect. Thank you.
1 second. Yeah, it is doing it right now. Okay, perfect. Thanks for letting us know. So yeah, so like not only we have like the Milky Way in this figure, but we also have like data right here in this figure for the large and small Magellanic clouds, which are these galaxies right here. So you can imagine that you can also use these proper motions and this astrometric information in this dwarf galaxies, and we can learn something about them by just having like precise motions for the stars. We can learn something about the kinematics inside the systems. So this is one way to go about this. And then, of course, one of the mandatory plots for us to show when we are talking about dwarf galaxies is about the discovery timeline for dwarf galaxies. So these two monstrosities right here, the small and the large Magellanic clouds, they were known since antiquity by people in the southern hemisphere of the globe. However, all of the other dwarf galaxies have been discovered over the last century or so. And this is like this timeline that I just mentioned. So of course, the Magellanic clouds have been known since like antiquity, but then all of these other dwarf galaxies right here, this like really slow development in the number of satellite galaxies that we know around the Milky Way, it was really driven by just photographic plates, just looking at overdensities of stars in photographic plates. But then when we started having large area sky surveys, specifically here around 2005, we started having data from this low and digital sky survey. The number of satellite galaxies that we discover around the Milky Way really skyrocketed. And like we now know, and this second jump right here is because of the dark energy survey. So in total right now, we know about 50 like satellites of the Milky Way that are confirmed to be like not only real systems, but real dwarf galaxies. There's a bunch of like ambiguous stellar systems that we don't know if they are actual globular clusters, star clusters, or dwarf galaxies. So this is kind of like the current situation. And then, yeah, so this is kind of like the direction of discovery. We are first discovering like this brighter dwarf galaxies, that's what I'm calling right here. So these bright dwarf galaxies like the LMC and the SMC. Of course, you would believe that the most luminous galaxies will be discovered first, and this is exactly kind of like how it happened. And then we have like the discoveries of what we call dwarf spheroidal classic satellites around the Milky Way. So Fornax and Sculptor are these two galaxies right here. They are kind of like in the intermediary range, in this intermediary mass regime between the bright dwarf galaxies, which is kind of like the SMC and the LMC, and they are these dwarf spheroidal galaxies. They are in between from the bright monstrosities to the really, really tiny dwarf galaxies, which are this, for example, this one galaxy right here, Pictoris 1. And throughout the talk, I'm going to mention another ultra-faint dwarf galaxy, which is Pictoris 2. So these really are like very small stellar systems. If you think about like in terms of like their stellar mass, these things have a few thousands of solar masses of stellar mass. So these are really probing the extreme regime of like galaxy formation. So then, but why do you care? So I guess one way to put this is this figure right here. Of course, these things are all connected, but I wanted to like display it in this way. So these are many reasons for why we would like to study dwarf galaxies, and hopefully one of these appeal to you guys. So first of them, we can use, like, for example, galactic dynamics. So measuring motions and radial velocities inside these dwarf galaxies to learn something about dark matter. So these dwarf galaxies, because of the steepness of the stellar to halo mass ratio, these dwarf galaxies are really the most dark matter dominated systems in the universe. So we can actually learn something about the nature of dark matter by studying the motions of stars inside the systems. And this is what many people here actually do. And another thing that we can actually do from these dwarf galaxies is because we are really probing the extreme low mass end of galaxy formation physics and the galaxy formation process that we know. So one of the things that I mentioned during the lunch with the grad students was that one of the main like topics that are like is like really being like pushed forward right now in the community, like in astronomy in general, is just understanding galaxy formation, right? Understanding the formation and evolution of galaxies. But what this really means, at least for me, is that we really want to have like a theory of galaxy formation that can produce from the brightest galaxies inside the centers of galaxy clusters all the way to the minuscule galaxies, which are these ultra-faint dwarf galaxies. And then finally, we can also use dwarf galaxies because their stellar populations are simple enough. We can actually use this as laboratories to understand chemical evolution and nucleosynthesis. In particular, one topic that I'm really interested in is that because these dwarf galaxies are simple enough, you can actually distinguish different sources of like chemical enrichment in these dwarf galaxies. And then you can really probe what is the origin of chemical elements. And also all of these things like actually connect to each other. But these are kind of like an idea of why you would like to study dwarf galaxies. And then, so this is one, of course, there are also challenges and problems with this. So this is one example of a problem that I think is like really illustrative of like the kinds of things that are still challenging for us to understand in terms of galaxy formation in this extreme low mass regime. So what this is showing in the horizontal axis is just the stellar mass for different dwarf galaxies, both in simulations and also observations. So the observations are the squares here, and the simulations are the colored dots. And in the vertical axis is the half-life ratio, the half-life ratio radius of these galaxies. Sorry about that. And what this is showing is actually that the simulations, they can actually reproduce quite well this relationship. By relationship, I mean, what is just happening is that the more massive galaxies are just larger. This is essentially what is happening. And so although the simulations can kind of reproduce the broad trend where more massive galaxies are larger, what happens is that we actually have like some outliers that are very difficult to explain with the galaxy formation models that we currently have. So I think we should highlight, for example, this one galaxy right here. This is the most extreme example of a very compact dwarf galaxy. So this galaxy M32 is actually a satellite of Andromeda. And like it is right here in this little figure, there's actually the Andromeda, like the M31 disk right here. And this satellite of Andromeda is really, really compact. And there are no set of simulations that can actually reproduce the compactness of this galaxy. On the other hand, we also have these extremely, very diffuse dwarf galaxies. So these things up here, they are also very difficult to produce with the galaxy formation models that we have. So these galaxies, specifically during this talk, I'm going to highlight a lot this Crater 2 dwarf galaxy, but there's also this other galaxy right here, which is called Andlia 2, and this other galaxy here in between them, which is another Andromeda satellite, which is Andromeda 19. So these three, this set of galaxies right here is also very difficult to explain with the galaxy formation models that we currently have. So that's fine. However, like we actually kind of know, like there are actually propositions for how you can produce this very compact dwarf galaxies. One of I don't know exactly if this works for specifically this one system, but for example, in galaxy clusters, what people argue is that these extremely compact dwarf galaxies could be produced by just stripping the stars out of galaxies that are nucleated. So if a galaxy has a nuclear star cluster, this will be just the remaining nuclear star cluster that was left over after extreme tidal disruption of the systems. But then these things are here are actually a bit more mysterious. And then this is kind of like how we can actually, like, just this figure is just to highlight how extreme these objects are. So this is the LMC, and this is that N-2 galaxy. In these galaxies are so extremely diffuse, like this N-2, for example, is so extremely diffuse that it essentially has the same size as the Large Magellanic Cloud, but it only has 1/1000 of its stellar mass. So it's like really, really extremely diffuse. And again, how we even know that these things are real, right? So this is how Gaia comes in, for example. So whenever we are looking for these dwarf galaxies, really the way that we actually find these systems, you're not just looking for overdensities on our overdensities in space anymore. Because if you look for this one galaxy so diffuse that you would never actually find this galaxy if you were just looking spatially on the sky. But you can actually use color information, for example, to actually filter out or filter in the stars that you care about. For example, if you just scan your sky using, for example, this kind of idea, which is just using an isochrone filter, for example, you can just include only in your filter all of the old stellar populations that you care about, like metal poor and old stellar populations that would be associated with dwarf galaxies, for example. So by doing this kind of like scanning in the color magnitude diagram, what you're really doing is scanning in 3 dimensions, because you can not only scan on the plane of the sky, but you can actually also use the color magnitude diagram information to actually scan in the distance direction. That's cool. So, but also like this one galaxy had a major contribution from Gaia, because if you just look at Gaia proper motions, you just have like this blob of stars right here, which is just the Milky Way, because all of the stars in the Milky Way are just moving in a certain direction. You can see like this whole blob, which is just all of the stars in the disk of our galaxy just moving in one direction. And all of these stars right here, really close to 0, 0 in the proper motion plane, they are really the stars that are associated with this one dwarf galaxy. So not only we can see this overdensity of stars in the color magnitude space, but also we can also see that these stars are really moving together. So they really have proper motions that are commensurate with a cohesive stellar system, let's say. So that's nice. And then, so this is another way to see, this is just to, again, highlight how extreme these very, very diffuse galaxies really are. So what I'm showing right here right now is in the horizontal axis is the surface brightness of different galaxies, and specifically the color points are all of the galaxies that are galaxies in the local group or satellites, either satellites of the Milky Way or Andromeda. And in the vertical axis is, again, the half-light radius. This is actually like the half-light major axis for these galaxies, but essentially the size of these galaxies. And these right here, these gray points right here, is a class of galaxies that people in the literature call the ultra diffuse galaxies. So these ultra diffuse galaxies, they are really common not really common, because they were only like really kind of like, let's say, discovered, or they were like described in the literature maybe 10 years ago. And like these things, they are usually found in the environments of galaxy clusters. So in galaxy clusters where you have like severe run pressure stripping and tidal disruption happening because of like how dense these environments are, you can actually produce these things that have very extremely low surface brightness. However, these galaxies that I'm talking about, these satellites of the Milky Way and M31, they are really a lot more extreme. They are really local extreme analogs to these ultra diffuse galaxies. If you think about like in terms of surface brightness, these ultra diffuse galaxies that are about like 25 right here, and all of these satellites, they have surface brightness that are larger than 30 in magnitude per arcsecond square. So if you think about like how these things are like a lot more extreme, if you think about in terms of magnitude, so this is log scale on a base of like 2.5. So you go from 25 to 26, 27, 28, 29, 30, 30, then 2.5 square like power to the 5 is like approximately 100. So these galaxies right here, so these satellites, so these diffuse satellites of Milky Way and M31, they are 100 times more diffuse than the ultra diffuse galaxies, okay? So these are really extreme objects that cannot be explained from the galaxy formation models that we have. However, having said that, there is usually one explanation to how galaxies can be enlarged in lambda CDM. And the mechanism that we have in lambda CTM to enlarge galaxies is just by tidal disruption. So this is one simulation just to illustrate this. But when a satellite orbits, for example, its massive host, in this case, a satellite of Andromeda or a satellite of the Milky Way orbiting M31 or the Milky Way, they are really going to, like, because of tidal forces, because of the gravitational potential of the massive host, they are just start losing stars. And in this process, this tidal disruption process, they can be enlarged because of that. However, it just so happens that if you just perform just pure antibody simulations and you try to simulate the sizes of these galaxies and their velocity dispersions or their kinematic properties or their structure in general with just tidal disruption alone, it just so happens that it doesn't work. So this figure right here is from this paper by Archaeology from 2022. What this figure is showing is in the vertical axis, essentially the velocity dispersion, and in the horizontal axis is the sizes of these galaxies, so the half-life ranges again. And if you just think about it, this is another manifestation of the mass size relation that I showed you guys on one of the first slides, because this is again the size, and this velocity dispersion, you can imagine that the velocity dispersion is going to have something to do with the total mass of a given galaxy, right? The higher velocity dispersion systems are just more massive. So this is just another manifestation of the mass size relation. And then it just so happens that if you just get whatever you would expect from just lambda CDM alone, so if you just perform a nice dark matter only simulation and you leave your galaxies isolated, what you would have is like this red line right here or this gray band. But then if you also include tidal disruption in your simulations, you would get a limit of like this blue line right here or this blue band. And really, those extremely diffuse satellites, again, Anglia 2, Andromeda 19, and Crater 2 cannot be explained by tidal disruption alone, at least in this set of simulations. There's another Andromeda 25 satellite here that I don't have much to say about it. Okay, so however, this same group of authors actually proposed actually a lot earlier than that, actually before the first of these not before the first of these galaxies were discovered, but before Crater 2 was discovered, which was back in 2016, even before this one satellite was discovered, these authors had already proposed a method for you to actually enlarge your galaxies a lot more by tidal disruption, which is to combine tidal disruption with a different density profile. Instead of just having a cuspy Navarro-Franken-White density profile, which would be the red line, so this is a figure of just log density in the vertical axis and log radius in the horizontal axis. If you just make a dark matter only simulation, what you get out of lambda CTM is the red line. So this thing that we call the cuspy halo or the Navarro-Franken-White profile. But then if instead of starting your tidal disruption with like a cuspy halo, if you start with a core, these galaxies that have core halos, they are a lot more susceptible to being enlarged by tidal disruption. In the specific orbit of this galaxyCrater 2 that I'm going to like focus more, this galaxy by tidal disruption, if you assume that it's a cuspy halo, you can enlarge this galaxy by something like 25% in the specific orbit of this one specific galaxy. But if you assume that it's a core halo, you can enlarge this galaxy by a factor of 10 or something. So we really could explain, this combination of factors could explain the sizes and those very extremely diffuse galaxies that are those outliers in the mass size relation. So this is really good. However, why? So one of the predictions that I mentioned, like these authors again, so Archaeology again from 2015, what these authors actually realized is that if you just look in antibody simulations with different density profiles that are experiencing tidal disruption, so in these few dots right here, so these circles are the Navarro-Franken-White cuspy halo prediction from the simulation, and the triangles are the cuspy prediction from the simulation. What they realize is that if you actually measure in the vertical, this is what they're showing in the vertical axis, the velocity dispersion ratio between the center of the galaxy that is being disrupted, so the remnant of the galaxy that is being disrupted, and you measure the velocity dispersion also in the tidal stream that is being produced. This movie shows like very nicely these tidal tails that are being produced. If you measure, what they predicted is that if you measure the velocity dispersion ratio between these two components of this tidally disrupting system, you could actually kind of diagnose whether you have a core halo or a cuspy halo. And this is what it's showing right here. So if you make a prediction for what should be, and actually these simulations, I'm going to go back into this again, but like in these simulations, they actually do have an orbit even though they came before the discovery of this one galaxy that I mentioned in Crater 2, they actually had kind of a similar orbit to that galaxy. Essentially because in order for this to work, you really need a high eccentricity orbit, and you don't have many dwarf galaxies doing that. So it ends up that it just happens to work for Crater 2. So they predicted that this velocity dispersion ratio between the tidal stream and the remnant of the galaxy should be a lot higher if you have a core density profile. Okay, and so about a factor of 4 times difference in velocity dispersion ratio. So that's nice. So, but at the time, like we really could not apply this to any dwarf galaxy. We didn't know of any dwarf galaxy that would fulfill the conditions for this to work, which is, for example, being experiencing tidal disruption, of course, but also being like, for example, in a relatively eccentric orbit. But why is this not okay? Like why don't we just claim that yes, we have core halos for this very low mass dwarf galaxies, and this is just solving the outliers in the mass size relation. And it just so happens that it's very hard for you to transform your halo from the cuspy profile, the one that is predicted from lambda CDM dark matter simulations, dark matter only simulations alone, and transform that into a core. So this is one example of a plot that shows of how people actually in simulations, in hydrodynamical simulations, actually make this happen. So what this is showing right here in the vertical axis is the slope of the inner dark matter density profile. So essentially it's just a measurement of your central dark matter density in a given galaxy. And in the horizontal axis, and the horizontal axis is really what matters, is this ratio between the stellar mass and the halo mass of a given galaxy. What matters right here is that this gray band is the prediction from the Navarro-Franken-White profile. So the cuspy profile would be the gray band, and the blue band, or all of these little stars right here, these are all galaxies taken from different hydrodynamical simulations. In red is galaxies taken from these Nihao simulations, and the blue dots right here are taken from the Fire 2 simulations. So essentially what happens is that if you have a stellar mass to halo mass ratio that is pretty high, so for more massive dwarf galaxies, and this is the regime of the bright dwarf galaxies like the LMC and the SMC, you really can produce these cores, so these core halos, which are these galaxies right here. However, if you have a low mass galaxy, you cannot do that. And the reason for that is the mechanism that really happens in the simulation in order for you to actually lower the central dark matter density. So maybe I should have had like a figure to explain this better, but essentially what happens is this. In the simulations, whenever you're just having like multiple cycles of star formation inside like your given dwarf galaxy, what is happening is that by supernova feedback, you're just blowing gas out of the center of this galaxy and blowing the gas out of the center and into the outskirts of the galaxy. So what happens is like when you're blowing this gas away because of like just supernova feedback, what is really happening is that you are changing the gravitational potential of the system. And because of these gravitational potential changes or gravitational potential fluctuations, you are gonna also alter the density profile or the dark matter distribution in your galaxy. So this is how, if you have a galaxy that is massive enough, it had star formation enough to produce enough supernova to alter the dark matter density profile, this is when we are gonna see the core halo. This is what's happening for galaxies up here. And what happens for galaxies that are too low mass, they just don't have enough supernova blowing off for you to actually produce significant enough changes in the gravitational potential. So this is kind of like what's happening. Essentially, massive galaxies, they make a lot of stars, they make a lot of supernova. This is enough to change their dark matter distributions by this mechanism of just fluctuations of the gravitational potential. Okay? So, and Crater 2, so Andromeda 2 and Andromeda 19, which are the other diffuse outliers in the mass size relation, they actually are kind of like around here. So they are kind of like massive enough, like they are massive enough that it's not a problem that they have core halos from this mechanism. However, if you take Crater 2 is like well in the regime that you would not expect that this galaxy was massive enough to produce a core with just supernova feedback alone. So this is why it is like, this is why we just don't say that, yes, all of these diffuse galaxies, they have core halos, is because we don't know how to produce core halos in these low mass dwarf galaxies, essentially. So we have 2 questions actually to answer. If we go into the data, if we find a galaxy, if we look at Crater 2, which is this one galaxy right here, can we show that this is tidally disrupting? This is one question. And the second part of the problem is like, we also need a core halo to explain the size. So let's see if we can actually show that these two conditions are actually met. And we can actually find evidence of that in the data. So first of all, so how we do this, how we go about this, is to use data from this survey right here that is called the S5 survey. So S5, it stands for Southern Stellar String Spectroscopic Survey. So this is a survey led by Ting Li, former grad student here, and she's now faculty at the University of Toronto. And essentially what they do in this S5 survey is to just go after everything that is tidally disrupting in the southern hemisphere. So everything from tidally disrupting dwarf galaxies, from tidally disrupting globular clusters, but also everything that is kind of like these stellar strings that are also ambiguous. We don't know if they are globular clusters or dwarf galaxies. They just go after all of these things that are tidally disrupting in the southern hemisphere with spectroscopy. So this is why we have like this survey has this very weird footprint, this like narrow lines on the sky, because we are exactly looking at those tidal tails that we care about. And we even have a logo. So this is a serious collaboration. And then we've like also, okay, so like if we go out there with the S5 survey and we get spectroscopy for a large area around crater 2, can we find the tidal tails? And the answer is just yes. So they are just there. So this is positions on the sky, and these green dots right here in the middle is the core, or like the remnant body of the crater 2 galaxy. And in black is the footprint of the survey. We have this very weird footprint just because the telescope broke and we couldn't get more data. And essentially the string is just there. So if you just measure radial velocities and metallicities for all of the stars in this like large field of view, you actually just find that there's a bunch of stars that are associated with this galaxy. They are in this, like they form this morphology that is kind of like this string-like morphology on the sky, and they also have coherent velocities and coherent metallicities. So we just know that this thing is tidally disrupting. Actually, you don't need to actually do anything too fancy. When I was actually looking at this data for the first time, I just made a cut in radial velocity and a cut in metallicity, and the string just pops up. So it really is tidally disrupting. So this is cool. But then what we could do is maybe just measuring from the velocities that we measure from the survey, from the spectroscopy, we can measure the line of sight velocities, both in stars, in the center of the galaxy and in the string. And we could maybe make that measurement of the velocity dispersion in both components and see what we find related to the ratio between those. And this is what I'm showing right here. So this is what I was just explaining. We just find that these stars, they have a very clear velocity gradient with position on the sky. This is just phi1, is just like coordinate transformation, just for convenience. And then we can actually measure the velocity dispersion on the string and the velocity dispersion in the core and see what happens with the ratio. So just a reminder, if the ratio between the velocity dispersion in the string and the velocity dispersion in the center is really high, this would favor the core halo profile. And then, so this is okay, so another thing like before that, sorry, I was hyping it up too much. So just another thing before that, because I'm gonna go back to this. This is an actual model that we calculate for the string. And one of the things that I just wanted to highlight that is kind of like interesting, the GIF is not running, but anyway. So one of the things that I wanted to highlight from this model, this is the model of the tidal disruption of this one galaxy crater 2, is that if you include the LMC and with and without the LMC, the morphology of the tidal tails actually change from the perspective of the sun. And the reason for that is not because the LMC is perturbing the stellar string, but really because the LMC is approaching the Milky Way. And because the LMC is so massive, when it approaches the Milky Way, it is actually pulling the Milky Way out of its original center. So the Milky Way and the LMC system, they are really orbiting the same center of mass. So because the Milky Way is actually being pulled away from its original location by the LMC, this is why we see this relative difference between the models with and without the LMC. So this is going to go back, come back later.
Yeah. So you deemed those stars, like in what you're calling the tails, to be members of crater 1, those big orange on the right hand side. Sorry, those big green circles like out in the tails. Yeah. So you deem those to be members of the galaxy. Is that just based on this is kind of like a chicken and an egg argument a little bit, right?
Yeah.
I mean, so is there any other information you have besides kinematics to tell you that?
So what I use to model both the galaxy and the foreground, what we do is just like including a mixture modeling thing, not only the information about the radial velocities, but also the proper motions and the metallicities that we measure for the individual stars.
The foreground has been subtracted.
Yeah, exactly. So we model the foreground and the galaxy all at the same time, and then extract that. So then, so finally, for the measurement that we really care about, so this is the final like PDF. So this is that quantity that I just mentioned. So the velocity dispersion in the string and the velocity dispersion in the center of the galaxy. And in green is the thing that we get out of the model that I just mentioned. And so essentially the value that we get somewhere like between 2 and 3, like closer to 2.5 or something. And the original prediction from the Errani 2015 paper is something closer to 1. However, by talking to these authors, so Raphael Errani himself, like they mentioned to me something that I was actually not aware of like until like 2 weeks ago, which is that in their model, actually, there are a bunch of like simplifications that can make a difference. For example, the gravitational potential of the Milky Way that they assume is just a spherical potential. And when the Milky Way, really, you should assume something that at least includes a disk, so an axisymmetric potential. And that can make a difference. So this is why we also have the green, the orange line right here, which is an any-body model that we run with the specific orbit of crater 2 and including all of these effects. So not only assuming that the gravitational potential model for the Milky Way is axisymmetric, it has a disk, but also including the LMC. And what we get is this value closer to 1.4. So we still don't have the any-body model for the core halo. But essentially, I think what I'm getting at is like, the question that we really want to ask is like, not what is the density profile, but really, can we reject the hypothesis of the cuspy halo? And I think at this point, I'm gonna say that we can like, if you just take this PDF, you can kind of reject this cuspy any-body model at the level of like 2 or 3 sigma. So this is like to the best of like, the best of what we can say is this so far.
Sorry, can I ask another question?
Yeah, go ahead.
I could go back to it, please.
Sure.
Yeah, so there's like 4 stars, 5 stars in each parts of the stream, right? So where's the stream and where's the core?
Okay, yeah, that's actually a thing that matters a lot. So essentially, the string is everything that is. So for those predictions from that paper specifically, what they did is to take the string to be everything that is outside 1 half-light radius. So if we do that right here, this will be like all of these stars right here would be all of the string.
Okay. My original thought was like you have like 4 stars in the stream, so
we have
sigmas, like,
we don't have a lot of stars in the string. That's why the ratio is like this really broad.
So that histogram that has those
yeah, that is yeah, exactly. And we have like about 20 stars in the string, so that's not a lot. Okay, but this is the best that we could do. So so far, why I think this matters is exactly because we don't know. Like, so having a core halo would solve the mass, like this being an outlier in the mass size relation. However, this would produce another problem, which is like, we do not know how to produce these core density profiles in galaxy formation simulations, okay? So this is where we are at. So I think another thing that we are doing right now in terms of like this system specifically is going out with getting more photometry. So what we are doing actually is tiling all of this region around the galaxy and the string with this survey that is called the MAGIC survey. That's like an awesome name for a survey. And what we are doing with this survey is doing metallicity sensitive narrow band photometry to just find the members out of like from metallicities alone and proper motions alone, and trying to find what is, and trying to ask the question of what is the extension of the string, which could also inform us something about the original dark matter density profile. I think I'm gonna stop here and ask you guys if you have any questions for this part of the talk. And I can move on to talk about like this MAGIC survey thing.
I'm a little confused on what this, you have a histogram of a probability type. Yeah, so what exactly is this is this a posterior?
Yeah, it is.
I see. And then how do you know that it's accurate?
What do you mean by accurate?
I mean, what if it's not that accurate?
Are you asking if there's like some systematics or something?
Well, how do you know that this, what you're getting here is like the correct posterior?
I don't think I know exactly how to reply to your question. Like this is like that would depend on, for example, the modeling that you make. Like for example, if you define your string to be like somewhere else instead of the position that we specifically assume for this specific model, that would change a little bit the posterior. So
can you sample the posterior directly or?
Yeah, that's what we do.
Oh, I see. So you
The width
actually
of that
just-
is-
Yeah,
this assumption.
I think if your answer is like, if you like, I guess the question would be like, how do we know that the model is correct? Because we are assuming like some model for the mixture modeling thing. Essentially, like what we do is just try a bunch of different models and say, can like essentially, I guess the scientific way to go about this is like, can we falsify or detection? Or like, can we falsify that hypothesis? And like, we just like, for us to do that, we just try different versions of the ways to modeling, like for modeling this thing, and then we essentially cannot get rid of it.
You can sample the posterior directly.
Yeah.
With just sampling. You don't have to use MCMC or anything.
Yeah, this is MCMC.
That's my point.
Ah, okay, yeah.
Yeah. So I mean,
This is
how do
MCMC.
you know that this is actually right? I mean, because MCMC actually is a little bit unreliable.
What do you mean by that?
I mean, which algorithm did you use, or did you do anything to check that actually this posterior you're getting here is?
Yeah, the way that I check this is just by like trying different versions of the model. Like for example, different assumptions of the model. For example, how do we separate from string and core? For example, this is one assumption of the model. So the way that I went about this is just.
Yeah, I understand. No, so I understand. I just mean like actually when you actually run it on a computer, how do you know this is accurate?
Well, this is like the best that we can do. I guess this is like this would be the answer.
Okay, great, thanks.
So like if we get more than it is very possible that we never, instead of having 20 stars in the string, when we have 200, we're gonna like get, maybe we can like, we're gonna have something better, but like this is the best that we can do so far.
Can I ask, this is going like way back to when you were explaining why sometimes the dwarfs can produce a core versus not. And you were like, okay, as we get to those bright ones, they're at the peak. It's because they basically always have a supernova go off that is able to scour out the core and make it be.
They have multiple supernova.
Yeah, exactly right. So I guess my question is like, as you go towards the lower mass and off to the left there, why doesn't it just like spread out in dispersion? Because like sometimes you get a supernova, most of the time you don't, but on occasion you do.
Yeah, if you like, for us to actually go into that regime, you have to be like a lot lower mass. So all of these systems, they have like, you are sampling enough of your IMF to kind of like have like some reasonable amount of supernova. But indeed, like
So even these ones on the left have had multiple supernovae probably.
Yeah.
Gotcha.
but you're actually right. Like for example, if you just go back here, if you have like a single supernova, for example, or no supernova, you would just have like the cuspy profile, which is just coming from the cold dark matter. Okay. All right. So now I wanted to move to talking about this magic survey and what we can do with this technique of photometric metallicities. But specifically, what I'm going to get at is how to. We're going to talk more instead of continue talking about dynamics. We're going to talk now about nucleosynthesis and formation of chemical elements. So, all right. So, what is this magic survey? So, this magic survey is a survey that is organized within the larger survey that is called Delve. So MAGIC stands for Mapping the Ancient Galaxy in Calcium H and K. And the reason for that is because we use this narrow band calcium H and K filter, which is shown right here, which is like sensitive to metallicities in order for us to actually measure metallicities directly out of photometry. And with that, we can do a lot of different things. For example, in Crater 2, we can select which stars have like low metallicities that are plausible members for that galaxy, for example. And so the main goal of this survey is not only to look at dwarf galaxies, although this is one of the main parts of the survey is to look at dwarf galaxies, but one of the reasons for this survey is for us to really find in the Milky Way itself and also the dwarf galaxies, its satellite galaxies, stars that have very extremely low metallicity. This was the main driver of the original proposal of the survey. And the reason that we care about that is essentially because if you get to very low metallicities, you are probing something that is directly, for example, might be directly associated with the nucleosynthesis that was happening, for example, in the first population 3 stars. So this one was the main driver for the survey originally. And then, so this is how we do it. I think this is a really interesting plot to show. So this plot on the left, so this is just a color plot. And what is showing here in the horizontal axis is G minus I color. You can think of this as directly related to the temperature of your stars. And in the vertical axis, you have some bizarre color combination that includes the photometry from this calcium H8K band that we are getting with the MAGIC survey. And essentially, like for a given surface gravity or for a given luminosity for your stars, you can actually compute models or like stellar models that actually reproduce these colors in order for you to, by locating your star in this space, you can actually infer what is its metallicity. Essentially, you just like interpolate across these models, and if you have information for all of this photometry, you can kind of infer the metallicity for your stars. And this happens to work really well, especially for dwarf galaxies. So this is one paper that we just published. I think it's like accepted right now. I don't know if it's published already, but it is on the archive. But what we did in this paper was to study one of these dwarf galaxies, one of those dwarf spheroidal galaxies that is called Sculptor. And using these photometric metallicities, we get a very good agreement. Photometric metallicities are on the horizontal axis. We have a very good agreement with the spectroscopic ones, which is in the vertical axis. So yeah, it just works really, really well. So why I think like this is this is very successful in not only studying the stellar populations in a given dwarf galaxy, but it's also very useful for you to find like these extreme objects with like very extremely low metallicities. And this is what is shown right here. So why do you care about like finding this like extremely low metallicity stars? And I think this plot is like very good from this paper that we just published from the MAGIC survey. And what this is showing is in the horizontal axis is the iron abundance for different stars. And this iron abundance is essentially just your proxy for overall metallicity. And in the vertical axis is the carbon abundance. Carbon is like really critical here for reasons that are going to like hopefully make sense right now. Essentially what is happening right here is that when you get to metallicities that are really, really extremely low, so in this scale, this is a log scale in comparison to the sun. So if this scale is at 0, which would be like somewhere around here, this would be the solar metallicity. At -1 is 1/10 of the solar metallicity. -2 is 1/100. And then if you're at -4, is 1/10,000 the solar value, the solar metallicity. And when you're like in this regime of like this extremely ultra metal poor stars, what happens is that these stars at such extremely low metallicities, they are probing their nucleosynthesis, their chemical abundance patterns are essentially probing order of 1 supernova. So a single population 3 supernova can produce all of the heavy chemical elements that ended up like in this ultra metal poor stars with metallicities at -4 in this scale. And it just so happens that these stars that have ultra low metallicities, they tend to be like very rich in carbon, which is like shown all of these stars right here. They have very high carbon abundances. However, the one thing that I wanted to take out of like this figure is that if you have the complete abundance patterns for a given star that had all of its elements coming out from a single supernova, if you have a model for your population 3 supernova, we can actually compare the elements that are being produced in your model to the chemical elements that are actually measured in this ultra extremely low metallicity stars. And by making this comparison, you can actually infer something about the properties of the original supernova or the original progenitor stars for those supernova. And this is exactly what is happening. If we make like this comparison, this model comparison for the stars that have very high carbon abundance, they tend to be blue in this figure, which means that they have somewhat of like lower explosion energies. So this is what blue, essentially all of the blue points right here, they have their original supernova have low explosion energies and they produce a lot of carbon. And if you go to these stars right here that have low amounts of carbon, they have this tendency of having like high explosion energies, really shown with the yellow point right here. So essentially, this is why we care about like finding these extremely metal poor stars, is because by measuring the chemical elements in their atmospheres, we are actually inferring something about the properties of the first population 3 stars. That is nice. However, we have already found a bunch. So why do we need more? And so one of the reasons is because we don't actually only want to look at this ultra and extremely metal poor stars in the environment of the Milky Way, but we really would like to probe different environments. Like for example, what happens with the first star's nucleosynthesis and what is the chemical evolution if you're getting like something like a dwarf galaxy or a different environment from the Milky Way. And it just so happens that in this same paper, we found a bunch of stars. We were just like getting high resolution spectroscopy and abundances for a bunch of stars that are of like this extremely low metallicity kind in the MAGIC survey. And it just so happens that just by looking at stars that are extremely metal poor in the outer halo of our galaxy, we found a bunch of them coming from the LMC. So this is why we go, well, this is when we go back to the figure that I showed, where the LMC, when it is like as it is falling into the Milky Way, it is actually perturbing the halo of the Milky Way, and also stars from the LMC and the SMC are being stripped out of these galaxies. And this is what is shown right here. So this is just an angular momentum distribution. This is angular momentum in the y direction. This is x direction. You can think about like a Cartesian frame with the galactic center in the center, in the origin of your coordinate system. And it just so happens that we found a bunch of like this, out of 6 stars that we were looking at, half of them, so 3 of them, were actually, they have extremely high angular momentum values. And this is something that we can only measure, or we can only calculate because we have proper motions from Gaia. And they have extremely high angular momentum that is commensurate with coming from the Magellanic clouds. So this is one thing that I think is interesting, is like not only the LMC is perturbing the halo of our galaxy, but also stars are being stripped out of the LMC and the SMC, and they are like being incorporated into the Milky Way. But then, so this is cool. And then if we go back to this figure, actually, now it's not talking about like the MAGIC survey directly, but actually, since I mentioned that we would like to probe different environments with these extremely ultrametal poor stars, actually, we have found a couple of these ultrametal poor stars in the LMC itself. So this one star right here with like an iron abundance close to -4, this was discovered in this paper from last year, this GD 2024 paper. This is from postdoc now at Stanford, Ani Chidi. We discovered this one star that has a metallicity like this iron abundance of -4, extremely low metallicity. And just this year, I published a paper where we found this one star right here. This is closer to -5. This one star is actually a star from the Milky Way, but when integrating the orbit backwards in time, this star actually ends up going back into the LMC if you consider a gravitational potential that has both the Milky Way and the infall of the LMC. So both of these stars, they have extremely low metallicities, but they are not carbon enhancement. So enhanced. So this is one thing that is like worth like noting, is that all of the essentially all of the stars, if you go like below -4 point something, essentially all of them have very high carbon abundances. But these two stars that we found in the LMC, none of them is like very carbon rich. So this is something like, this is to say that maybe the chemical enrichment by the first stars is environment dependent. So, okay, so like how do we, like this is the integration of the orbit backwards in time. So this is again Cartesian frame. So this is Z coordinate. So the distance from the position with respect to the galactic plane. And this is Y position in this Cartesian plane. And in red is the orbit of the star that we found that is like actually part of the Milky Way now. But if you integrate the orbit backwards, it actually ends up like going back to the LMC or to the halo of the LMC. And this other star in yellow is the other star that is the other ultrametal poor star that it is just a member of the LMC. Okay, so this is another thing that we can actually do, is like probe different environments using like this, using Gaia. We can actually find stars in different environments that have like these extremely low metallicities, and see if they are similar to the Milky Way. And so far, we are seeing that at least in the LMC, it doesn't seem to be that these extremely ultrametal poor stars are carbon enhanced. So maybe the chemical elements that are being produced by the first stars, they have some environment dependence. And indeed, this is kind of like the final point, which I think there actually is an environment dependence. And this is another ultrametal poor star that we just recently discovered in the MAGIC survey. So this one star right here. So in this is essentially a similar figure to what we are looking at before. But instead of having iron in the horizontal axis, we actually have calcium, because this one star is so metal poor that we cannot detect iron lines in its spectrum. And in the vertical axis, instead of like having, is just the carbon abundance again. However, this is in the ratio with calcium. And essentially, but this one ultrametal poor star that we actually found in a third different environment, not in the Milky Way, not in the LMC, but in one galaxy that is called Keter 2, and this one dwarf galaxy is one of those ultra-faint dwarf galaxies. And if you take the mass-size relation, we can see that there's this group of like very faint satellites, very low luminosities, very low stellar masses, like stellar masses of close to 10 to the 4 solar masses in stellar mass. And so this ultra-faint dwarf galaxy, it has this one star that we discovered that is in this ultra metal pool regime that is probing the nucleosynthesis out of the very first stars. It is actually very carbon rich. So wrapping everything up, what I think is happening is the following. So I mentioned that the high carbon abundances are associated with low explosion energies. So what I think is happening, or what I think we are getting at, is that these very first stars, this very first supernova, they could have like a similar explosion energy distribution to the supernova that we observe right now. However, those supernova that have very high energy, if they explode in this very low mass galaxy, the gravitational potential of this very tiny ultra faint dwarf galaxy is not strong enough to hold all of the material that is being ejected out of this like very energetic supernova. However, if you have a very low energy explosion, so if you have an explosion that doesn't have enough energy to blow all of the material out of these like very tiny dwarf galaxies, you can actually retain that material. So that's how these very tiny ultra faint dwarf galaxies, they can retain the material that is being produced by these low energy explosions. And the main signature of that is very high carbon abundance. On the other hand, if you have just a regular explosion energy distribution, but now your explosions or your supernova are going off in more massive galaxies, like for example, the LMC, what is happening is that because you have an overwhelming amount of high energy explosions in comparison to the low energy explosions, all of your carbon, your excess of this signature of excess of carbon is just being swamped by a bunch of like high energy explosions that are being also incorporated into the interstellar medium. Okay, so I think basically the bottom line here is that there really is an environmental dependency on the chemical enrichment by the first stars, the first population 3 stars. And this is because different environments can hold the material that is being produced by the first supernova depending on the explosion energy of that. So this is essentially what we are getting at. So yeah, I think I'm gonna stop here and ask if you guys have any more questions about the second part of the talk. And yeah, thank you.
I'd love to hear more about the explanation here. So has it been a statement about at that point, or a statement about the mass of the first supernovae, the percentage?
Even if you're in a regime that you're not stochastically sampling the IMF, even if you're like sampling the full IMF, what happens is that if you just think about like, even if the energy distribution of your supernova is the same in both environments, what happens is that these really tiny galaxies, they are just not, the gravitational potentials is just not like strong enough to hold the material that is being ejected out of the more energetic explosions. So that's why all of the material is just lost. It's just blown out of the galaxy. And then if you have a very low energy explosion, these tiny galaxies can actually retain the material that's produced by these low energy explosions. Right. But the low energy explosions produce a lot of carbon.
Sure. And so is that telling you something about the nature of those first supernovae? I mean, they must have lower energy for some reason, right? They're not just 10 to the 51 or.
I don't think so far, like because so I guess one of the things that we are getting at is like it's very difficult to extract information, environmental information about the actual properties of the first supernova, exactly because on the things that we actually observe, which are the chemical patterns of the second generation stars, the chemical patterns that we observe actually depend on the environment. So if we are, for example, like in the Milky Way, we observe a lot of like these very carbon-rich stars, which are these stars right here. So, but what might be happening is that these were not stars that were actually produced like in the Milky Way itself. They actually were accreted out of, for example, ultra-faint dwarf galaxies. So I guess what we are getting at is that we do have this environmental dependence on because of the energetics of the supernova explosions. But I guess another thing that we are getting at is that it is actually really hard for you to have a fair sample to actually reconstruct the properties of like the global properties of the universal properties of all the supernova, the first supernova.
Okay. So you said you have this test about the core versus the stream and velocity dispersions. Has anyone done that on Sagittarius?
I think it is like, it doesn't work for Sagittarius because Sagittarius is close to Earth center.